Hi everyone, this video to present a paper titled Smart Soft Open Point Architectures and Power Control Management between Light DC Railway and Low Voltage Distribution Network to be presented in the online Power Electronic Machine Drive Conference. Starting with the preface of the paper, this paper proposes a new smart soft open point architectures based on the power electronic converters to interface between the light electrified DC railway network with the low voltage grid distribution network. Considering the different dynamics characteristics of the two networks, a DC bus in the smart soft open point is used to connect an energy storage system to allow a decoupling of the power flows between the two networks. The new smart soft open point is capable to capture the regenerative braking power from the rail and use it to support the low voltage distribution grid and charge the battery. Similarly, the excess of the renewable energy source power generation in the low voltage grid can be also stored in the battery in the electrical storage system if not consumed locally. This paper presents a 2 converter and a 3 converter topology for the smart soft open point to be analyzed through time domain simulation for different operational state of the train as well as different voltage and power level at the low voltage distribution network. Finally, a discussion and a comparison for the prospective architecture scenarios are provided with respect to their controllability, power losses, braking efficiency, cost, and finally the spacing. A schematic for a standard DC railway network is shown in this slide at the top, where a DC railway substation are supplied from a medium voltage AC network. The train operation can be categorized into 3 main modes: accelerating, coasting, and braking. The two figures at the bottom of the slide show respectively an example of the train speed and mechanical power versus time in the 3 main modes in sequence. A MATLAB Simulink model for this railway system shown in the figure at the top of the slide, where the railway power supply is modeled by a constant DC voltage Vs(N)L to represent the no load voltage of the DC supply with in series resistance Rrec to represent the voltage and the current output characteristics of the rectifier bridge at the railway power substation. The train in this model is simulated by a power controlled load current source based on the provided train power given in the previous figure. The rail resistance Rrail represents the combined resistance of the electrical cable of the electrification network as well as the return cable. Finally, the braking resistance Rp is connected in parallel through a switch controlled by the rail voltage Vrail in order to avoid any over voltage exist on the rail during the braking. The waveform of the rail voltage Vrail, rail current Irail, supply rail current Is, and the braking resistance current IRP are shown in the waveform at the bottom of the slide, where a shocked voltage is shown in the rail voltage waveform during the braking period of the train when the rail current is negative during braking. The proposed smart soft open point structure for the interconnection between the DC railway and the low voltage distribution network is shown as a figure at the top, where the smart soft open point has a 3 terminals configuration in order to connect to the railway network. the battery storage system, and also the distribution network. The low voltage distribution network under consideration operate at 400 voltage and can act as electrical load or electrical power source based on the electrical load in the network, either industrial or residential, as well as the renewable energy source available in the network, either coming from the photovoltaic panels or from the wind turbine. There are two control constraints have to be defined to avoid any power recirculation between the two networks in order to minimize the power losses. The first one is that the DC railway substation does not feed either the battery nor the public grid network. And the battery and the low voltage grid do not support the railway network. These two constraints are fundamentally implemented since one of the main objectives of this smart soft open point is to minimize the mutual losses in the railway and the public grid network. So, the proposed control strategy mainly investigates the benefit of utilizing the available braking power from the train to feed the battery or support the public grid, and the possibility of supplying the railway network from the battery or the public grid is instead less relevant, because they will have lower power rating and it will make lower effective contribution. Therefore, in order to analyze the functionality of the power electronic converter utilized in this smart soft open point, two different control scenarios are proposed, according to whether the public grid act as a load or act as a power sink. The first control scenario, where the grid act as a load and sink power, as shown in the figure in the left of the slide. So in this scenario, the public grid is acting as a load and it can receive any available power from the smart soft open point up to the grid maximum power constraint PG maximum, which is determined by the regulation of the provider of the public grid. So if there is no available braking power come from the train, the public grid will be fed only by the battery. However, once there is regenerative braking power come from the train, this power then will be used to supply the local grid up to PG maximum and also can charge the battery with its maximum charging rate. Priority will be given to feed the public grid rather than the battery to use the available energy direct in the load at the low voltage network, rather than like have power losses during the energy storage process. In the second scenario, as shown in the figure on the right, the public grid acts as a supply and it supply power to the smart soft open point where there is an extra power available from the renewable energy in the low voltage grid. In this case study, the renewable energy source is assumed to come from the photovoltaic, and this output power will be also assumed as a constant PGS during one mission profile of the train, which will be only take a few minutes long. Furthermore, it is assumed that the power PGS can't charge the battery up to its maximum charging rate. Therefore, during the braking period of the train, the braking power from the railway will contribute to charge the battery up to its maximum charging rate. The figure at the top shows the schematic for the two converter topology of the smart soft open point, in which the battery, which is the energy storage system, is connected directly to the common DC path without any additional converter. The MATLAB Simulink model for this system is demonstrated at the bottom of the slide. There are two controlling indicators in the MATLAB model. one for detecting the start of the train braking state, which is con 1, and the other to determine when the braking power is lower than the grid maximum power. The public grid and the inverter circuit of the SmartSoft open point are simulated as power-controlled current source, in which the grid power is governed by the control strategy described previously in the previous section. In this model, we use a model for lithium-ion battery cell, where the selected battery capacity for this study have been chosen to be equal to the available braking energy in this example, which is around 10 kilowatt hour. In the first control scenario, when the grid acts as a load, Bg max is assumed to be equal to 80 kilowatt. The figure at the left of the slide show the waveform of the rail supply power, the train power, B rail, and the battery power, BB, and finally the grid power. The schematic for the three converter topology for the SmartSoft open point is shown in the figure at the top of the slide, in which the battery is connected through another DC-DC converter. The MATLAB Simulink model for this system is given in the figure as the bottom, where the controlling indicator and the model of the grid and the inverter are the same as the previous case. However, the control algorithm for the additional DC-DC converter is based on a current control approach, depending on the charging and discharging rate of the battery according to its datasheet. On the other hand, the first DC-DC converter is now governed by a voltage-based control to output fixed reference voltage of 750 for this study during all the operational modes of the train. The Pg maximum for the first control scenario of this topology is also assumed to be equal to 80 kilowatt, similar to the first topology. Similarly, BGS in the second control scenario of this topology is also assumed to be equal 3 kilowatt, likewise the other topology. Figure of these slides show the waveform of the power of the railway supply and the train and the battery and the grid for the both control scenario, where the grid sinks power at the left figure and the grid supply power at the right figure. The energy and power calculation of the battery and the grid during the braking of the train are provided in this table for both control scenario under both SmartSoft open point topology. Furthermore, the storage energy and power into the battery, EB storage and PP storage, are also calculated by taking into account the power losses in the internal resistance of the battery cell. Finally, the train braking efficiency for both control strategy have been calculated using this equation, where the braking efficiency equal the power of the battery storage plus or minus P grid over P braking, where P braking is the train braking power, BP storage is the battery storage power, and BG is the grid power, and it is positive when the grid sinks power and become negative when the grid supplies the power. Based on these results, it shows that both topology have similar braking efficiency in both scenarios, where both of them have around 6.3 or 6.2 for the first scenario. However, for the second scenario, they have around 0.36. However, This efficiency don't take into account the power losses within the power converter circuit in the smart soft open point, where the 3 converter topology will has more power losses in comparison to the 2 converter topology due to the additional DC-DC converter. Also, in the 3 converter topology, the voltage of the DC pulse is very sensitive to any variation at the real voltage. Finally, additional cost and space are needed for the 3 converter topology for the additional DC-DC converter. On the other hand, the main drawback of the 2 converter topology is a possible reduced lifetime of the battery due to the high frequency current component generated by the 2 converter and will be connected to the battery. Also, this could be resolved by inserting a capacitor in parallel to the battery. For both topology, one of the methods to improve the braking efficiency is to increase the battery total capacity. In this paper, the capacity is equal to the total train braking energy, which is around 10 kilowatt-hour, but in the simulation shows that it's not possible to transfer all the energy of the braking to the battery because the power during braking become very high and it become more than the maximum charging rate of the battery, especially at the beginning of the braking energy. However, increasing the battery capacity will also increasing the maximum charging rate and also enable large portion of the energy to be recovered to the battery. However, this efficiency will be traded against the higher cost of the battery, so it is necessary to do more in-depth investigation on the optimal efficiency level on the system. Another approach to increase the braking efficiency with the same battery capacity is to only increase the maximum charging rate using different battery technology with higher power density. Some research have proposed that the maximum charging rate could be reached up to 5 times the C rate of the battery, and under this assumption, the braking efficiency is recalculated under this 5C rate, and for the first scenario, the braking efficiency reach around 10% rather than 6.3, and for the second scenario, the braking efficiency reach around 2.3 rather than 0.36. It is clear that further improvement can be obtained by combining the battery with other type of energy storage system like supercapacitor, but also the system cost will be higher. Finally, the conclusion. This paper proposed a new smart soft open point architecture based on the power electronic converter to interface between the light DC railway network with low voltage distribution grid. The proposed smart soft open point provides a power connection between the two networks to achieve several objectives, including reducing the power losses, maintain the stability of the low voltage grid. Different power management control approach have been presented in this paper according to different operational conditions of the train as well as different conditional state of the grid network. Thank you for listening and goodbye.